Our next speaker, Dr. Zsolt Kira, is an assistant professor at the Georgia Institute of Technology, branch chief of the Machine Learning and Analytics Group at the Georgia Tech Research Institute, and associate director of Georgia Tech's Machine Learning Center. His work lies at the intersection of machine learning and artificial intelligence for sensor processing, perception, and robotics, emphasizing the fusion of multiple sources of information for scene understanding. Current projects and interests relate to moving beyond current limitations of machine learning to tackle lifelong or continual learning and adaptation, as well as distributed perception across heterogeneous robot sensor teams. Dr. Kira has grown a portfolio of projects funded by NSF, DARPA, and the IC community. He has over 25 publications in these areas, several Best Paper Student Paper Awards, has taught several graduate and undergraduate machine deep learning courses at Georgia Tech, and has been invited to speak at related workshops in both academia and within the DoD. Please welcome Dr. Zsolt Kira.
All right. Good morning, everyone, and thank you for inviting me and giving me this opportunity. By the way, I do have 3 roles, and don't be impressed by that. That's just what happens when you say yes way too many times. So I will give a little plug. We do have a machine learning center at Georgia Tech, so if you have any people that want to take a nice Ph.D. program, either in your organization to really build them up, I do recommend it. Today I'm going to talk about kind of moving beyond current machine learning methods that are really have lots of limitations when deployed either on robotics, which is what I'm interested in, or in many other applications as well. So I don't have to belabor this to this audience, but obviously, machine learning, and now called artificial intelligence again. By the way, I never like to use that term. And it came back to me. It's largely been driven by really these deep learning and machine learning techniques that really use lots of data to be able to train them to give you some kind of answer for that particular question that you're asking. My focus in my research has been really to apply these things to sensor processing and robotics. So sorry about those 5 million jobs that somebody mentioned. Although I do believe that, really we are trying to not replace humans, we're trying to really augment them and allow humans to focus on the things that are much more difficult, which robots and machine learning systems, as you probably know, can't do yet. The way current robots, as well as all these other machine learning applications work, as you know, is typically supervised learning. So you feed in lots and lots of data. You have poor undergraduate students labeling these kinds of images over many months, saying this is a car, this is a person, this is a car, this is a person, many millions of times. And really, these are just examples, millions of examples, and we're trying to learn some kind of generalized model for those sets of examples, and that's what's called inductive learning. And there's lots of algorithms, but currently it's dominated by deep learning. If you went to my workshop yesterday, If you went to my workshop yesterday, I gave a full day-long tutorial on this, but really the key idea is that we're in machine learning currently, we often don't apply much domain knowledge. Really, we just feed in lots of data, and we give a very complex model that can be learned, and then allow it to really understand what features are important, for example, in that data to give you the answer that you want. And so, there's lots of advantages to that. We no longer need PhDs looking at, different modalities of data, text, images, and audio, and coming up with their own features, doing feature engineering. But on the other hand, it's really driven by the data that you give it, as well as all the labels that you have to give. And so, really, it only works when you're doing certain kinds of things that are limited. So you're optimizing these models for one task. Unlike humans, they can't, label things in images and play chess at the same time. we optimize or learn models completely separately across these different tasks. They can't deal with what happens when things change. So in robotics, when you learn a model on some online data and then you throw it on a robot, clearly something's going to change in the world. It's going to encounter some kind of edge cases, and it's not going to be able to deal with that because it wasn't in the training set. And then also, kind of there's a rigid model where we train something, and then we deploy it, and once we deploy it, it no longer learns. Clearly, this is not how humans do it, and clearly this is not going to work very well, not just for robotics, but I'm going to argue that really pretty much all the applications that everybody here is thinking about really will undergo changes over time after you deploy the model. And so you can either, sure, you can have many more undergraduate students or whoever across the world label more data as the data changes, or really what I'm going to argue for is developing algorithms that can continuously learn and adapt to new situations rather than doing that. And then the last bullet point, which is all the categories must be known beforehand. So really, you can't discover new things in your data. What you can do is train a model to discover the same things you know about over and over again in new data, but you can't discover new things. And so we really want to move beyond these kinds of limitations. These limitations certainly hinder large-scale deployment in robotics, but I'm going to argue that pretty much most things that you care about that involve streaming pieces of data that you have to analyze will undergo some sorts of changes that you can't anticipate. And obviously, Tesla and others have found out about this the hard way because clearly there are lots of edge cases, for example, for self-driving cars that just cannot be anticipated. So this is how we want machine learning to work in robotics. We want to integrate kind of really fine-grained pieces of information rather than kind of very coarse information in your data. You want machine learning models that continuously learn and adapt rather than just are rigid. And we want to be able to discover new things in your data rather than just rediscover old things that you've trained it for, as well as have what's called goal-driven perception, which is can you change dynamically your processing of how you're processing the data based on context or the situation or what your ultimate goal is. So these are not, I'm not going to say these are easy problems. We're certainly working on them, and there are already some solutions that exist. But I'm going to kind of go through one example of some work that my lab has done in this area. And really what we're interested in is what fundamental kind of principles for machine learning are necessary to enable this kind of reasoning, which it doesn't exist today, but certainly exists in humans. The first, or kind of the example that I'm going to be talking about is what's called cross-task or cross-domain learning. And the idea here is, sure, you train your model, let's say, to detect all sorts of cars in images or classify them, but now we want to classify or detect motorcycles. And we want it to be able to do that without having any labeled examples for those motorcycles. We just want it to understand what cars look like and then obtain new data and then be able to say, well, this is some new object that I've never seen. Can I build a model for it using unlabeled data? The other situation is on what's called domain shift, which is what happens when the data changes. So you're training the self-driving car during the summer and all of a sudden there's snow everywhere. It will fail if you don't adapt to those changing statistics. So the problem of having unlabeled, unknown categories is very difficult. Again, this is not a solved problem, but one that we're working on. And so really, we're going to propose some methods, namely clustering through deep learning, that can solve some aspects of this. And the key idea is very intuitive. The key idea is rather than learning how to classify all these different objects in your data, we're going to learn really just how to compare things. This is very intuitive and actually is something that humans can often do much more easily in terms of when they give you labels. They can often say these two things are similar or these two things are dissimilar much more easily than saying this is, whatever species of a cat. And so this is going to be the kind of overall workflow that we use, and I'm not going to go too much into it, but really what we're doing is we're converting label data that has a set of number of categories to just a binary function that says these things are similar or dissimilar, and then we're going to apply it to unlabeled data, and now completely unlabeled data, you know what's similar and what's dissimilar. This is going to be very noisy because we transferred it from a completely different set of things. And so we developed some deep learning-based clustering algorithms that are able to take those noisy estimates of what's similar and dissimilar and group things that are alike together. And so now you've essentially learned a classifier for new things that you've never seen in your training data set before. So I'm on the academic side, so we publish papers using very simplistic data sets such as handwriting, and this gets state-of-the-art results. But more importantly, one of the key things, as you know from clustering algorithms, is that you often don't know how many new things are in your unlabeled data. And so what we've shown is that we're actually able to not just group things that are alike, that are new, but also we can discover how many intrinsic new things are there in your unlabeled data sets. And so, again, we can do that using state-of-the-art. And then we've actually, more importantly for industry, applied this for much more larger scale data sets, such as ImageNet, which you may have heard of, where we actually take, 30 new, we train it on, let's say, 800 categories, but then we take out 30 categories you've never seen before. Again, this is very complex data, high dimensional, and so on. And we're able to, unfortunately, you probably can't see it, but we semantically group things. So there's like birds and other kinds of things there. And then we're also able to cover this other case, which is called domain adaptation, where the statistics of your data changes, where, for example, you have some data, training data that you labeled, taken from a DSLR camera or something, and then you're applying it to some low-cost sensor. And the point is you don't have any labels, or you have a small number of labels in that low-cost sensor. And so we've shown that you can actually take this model and transfer it and actually learn better than the state-of-the-art for these new kinds of things. And overall, what we're trying to move towards is this really, again, dynamic thing where you essentially you can train whatever model you want, given the data you have, but then we want to discover new things as you get streaming data, streaming pieces of data that may be new, that may have completely unknown things, and so on. And so we continue to cluster them or group them together, and we learn classifiers for them. This is showing some example of a real-world video data set that we are applying this to. It's, again, hard to see, but this is just kind of some video from a self-driving car type sensors. And you can track objects through time. And so based on those tracks, you can actually then take all the things, all the objects that you know and they're seen. You don't know what they are. You group what you have trained in your models. So you know that these things are things that I know about because I've trained on them. And then you also can automatically cluster a group or discover completely new things that you haven't seen before. I don't know if this video is going to work. Let me try. I guess not. It's one of the good things about being in computer vision is you could show cool videos, but one of the bad things is the AV never works for playing them. Okay, well, if this video did play, what you would see is essentially that as the video progresses, we're able to automatically find completely new things in the environment. So we can find, things like doors and other types of vehicles that we've never seen in the training set. So we're basically discovering new categories of things. And so really, this is kind of the take-home message is that I want to convey is that really, sure, I know everybody's still trying to figure out how to work with supervised learning where we do have some data and the data is going to be always dirty and things like that. But really, moving forward, we want to think also about how to dynamically adapt to things. So we want to think about unsupervised learning, which is learning without any labeled data or small amounts of labeled data. We want to think about goal-driven perception, which is how do we actually not just do one thing at a time, but do multiple things at a time and change how we process the data based on that? We want to think about especially lifelong and continual learning, which is what I've been talking about really, where you're continuously adapting to new things. And that adaptation can be driven by some input from humans, obviously. And there's methods, for example, for machine learning to actually query humans. So they say, I'm not sure about this new thing. Can you tell me what it is so that I can learn from that? But the key idea is that we really don't want rigid models. And I think some of the issues that have come up with data bias, for example, have really conveyed that, where either the data set is not enough to really represent reality, or reality changes over time, and you really want to be able to adapt that. So that's really something that you really want to think about when you deploy systems that will work continuously over years at a time, because things will actually change in the world. And again, I've shown a lot of computer vision things because that's my domain, but this is totally applicable to other methods or other modalities or domains such as text, audio, unstructured data, and so on. With that, I'm going to conclude. But really, the message that I want to convey is I know there's been tremendous amounts of kind of progress being made. We now have actually working systems in computer vision. You did a lot of things in the past and then published a paper, but it didn't actually work. And that's why you never wanted to do a demo. These days, you can actually do demos, which is kind of cool. But despite that progress, there's still a lot of limitations, right, when we actually deploy these things in the real world. Some of these limitations are driven by this rigid train test kind of regime that we're doing. Some of this is driven by essentially not being able to leverage unlabeled data as much. But really, these are areas that we are pushing forward and trying to resolve. And interestingly, a lot of human intuition can often inform how we actually design these continuously learning systems, because humans are the best example of very adaptive, intelligent learning systems. And with that, I'm going to conclude. Thank you.